Have you ever wondered what happens when something that's moving perfectly straight suddenly isn't? Today, we're diving into a really cool physics puzzle. A charged particle, just minding its own business, flies into a magnetic field, and what happens next is pretty awesome. We're going to solve the mystery of that curve.
So here's how we're going to crack this case. We'll start with the mystery itself, this puzzling path. Then we'll uncover two huge clues, the invisible magnetic force and the basic physics of what makes anything move in a circle. After that, we'll smash them together to get one master formula, use it on a real-world problem, and finally, we'll crunch the numbers and get our answer. Let's do it.
All right, first things first. We have to set the stage. Let's get a really clear picture of exactly what's happening here.
Okay, so picture this. You've got this tiny little particle, maybe an electron, and it's just zipping along, straight as an arrow. Then, boom, it enters this magnetic field, and instantly, its path bends into this perfect, beautiful circle. So the big question is, what made it turn? What invisible hand just reached out and changed its course?
Well, that invisible hand? That's our very first clue. It's one of the fundamental forces of the universe, and it's the key to this whole puzzle.
It's the magnetic force. And here's the deal with this force. The thing that makes it so special, it always pushes at a right angle to the direction the particle is already moving. It doesn't speed it up or slow it down, it just pushes it sideways. Think of it like a constant gentle nudge to the side. And that nudge, over and over, is what forces it into a curve. The formula for it is simple too. Just the particle's charge, Q, times how fast it's going, V, times the strength of the magnetic field, B.
Okay, so we've got a sideways push. That's clue number one. But to really get this, we need one more piece of the puzzle. And this one has everything to do with the shape of that path, the circle.
And that piece is called the centripetal force. You've seen this a million times. Anytime anything moves in a circle, a planet going around the sun, you twirling a ball on a string, there has to be a force pulling it towards the center. That's centripetal force. It literally means center seeking. Without that constant pull inward, the object would just fly off in a straight line. It's the law of circles, basically.
So, let's take stock. We've got the magnetic force, which is giving our particle a sideways push. And we know we need a centripetal force to make anything move in a circle. And right here, this is where it all comes together. This is the aha moment.
Here it is, the big secret. They aren't two different forces fighting it out. In this situation, the magnetic force is the centripetal force. It's doing the job. That sideways push from the magnetic field is providing the exact center-seeking pull needed to lock that particle into a perfect circle. They're just two different names for the same thing here.
And if they're the same thing, well, then their formulas must be equal to each other. So we just take the magnetic force formula and set it equal to the centripetal force formula, and voila, we get this beautiful master equation. This thing is so powerful. It connects everything: the particle's charge and mass, the magnetic field, its speed, and the radius of its circle. This is the key that unlocks the whole problem.
Okay, enough with the theory. An equation is only cool if you can actually use it, right? So, let's get our hands dirty and apply this to a real-world problem.
So here's our mission. We've got an electron. We know how much energy it has. It's kinetic energy. And we know how strong the magnetic field is. The challenge is to use our new master formula to predict with total precision the exact radius of the circle it's about to trace out.
Let's just lay out everything we know. The problem gives us the kinetic energy and the magnetic field. And because we're talking about an electron, we know its mass and its charge. Those are just fundamental constants of nature. So look at that. We've got all the pieces. We're ready to go.
All right, game time. Let's roll up our sleeves and actually do the math. We're about to go from this list of numbers all the way to a final answer.
We're going to do this in 3 easy steps. First, we got to get our energy into the right units, joules. Super important. Second, our big formula needs velocity, v. But we were given kinetic energy. No problem. We can calculate v from that. And finally, step 3, we'll just rearrange our master formula to solve for the radius, r, and plug in all our numbers. Simple.
So, to find that velocity, we're going to use the classic kinetic energy formula. K equals 1/2 mv squared. We just need to do a little bit of algebra to rearrange it to solve for v. But first, and this is a really crucial step, we have to convert that energy from kilo electron volts into joules, which is the standard unit. Once that's done, we can just pop in our values for energy and the electron's mass.
And whoa, look at that number. That's 23 million meters per second. This little electron is absolutely flying. To put that in perspective, that's nearly 8% the speed of light. Insanely fast. And that's the velocity we need for our last step.
Okay, here we go, the grand finale. We take our master formula, and with a quick shuffle of the variables, we solve for what we want, the radius, r. That gives us r equals m times v divided by q times b. And now for the easy part. We just plug in all the numbers we know, the mass, that crazy velocity we just found, the charge, and the magnetic field strength.
And there it is. The math tells us the radius of the electron's circular path will be 0.0065 meters. Or, to make that easier to picture, that's just 6.5 millimeters. A tiny, perfect circle. We predicted it exactly. We did it!
So just think about what we just did. We started with a simple, almost mysterious question. Why does this particle turn? And by combining just two basic ideas from physics, we built a tool that let us predict its path down to the millimeter. That is pretty amazing. That's the power of physics right there.
So I'll leave you with one last question to chew on. Look back at our final formula. R equals mv over qb. What do you think would happen if the particle was moving faster? Or if we made the magnetic field way stronger? How would that change the size of the circle? The answer is right there in the math, just waiting for you to find it. Thanks for joining me.